Hello everyone and welcome back to another episode of the Hidden Quantum Champions. Today we're talking about a company called Qnami, and they are actually already building instruments using quantum sensors that can be used in today's labs and that might add value to tomorrow's chips. And if you want to understand how Qnami is building products that are using quantum to add value already today using quantum sensors, then you are exactly right in today's video, because we are going to dive deeper into Qnami. And if you want to stay on for today's video, make sure to get yourself something to drink, and let's get started right away on their website as per usual. So here we are on the website. It says Qnami up here with this fancy Q added in here. And you can already see the product, which is this, they call it Quantilever. I love the funny word joke. Discover our diamond probes with NV sensors. And that's basically, let's say, at the heart of the product. It is NV sensors that are integrated into atomic force microscope tips, more or less, and then hence into cantilevers. And we are gonna talk about these different products here that you can see in this carousel and the images that you can see throughout this video. But first, let's scroll down a little bit here and learn, let's say, the basics about the company. So it says, pioneer and leader in quantum sensing. Qnami is the world's leading quantum sensing company and pioneer in the development and commercialization of quantum technologies for sensing and imaging applications. We offer cutting-edge scientific instruments and analytical solutions for applications in nanotechnology, life science, and earth science. Our expertise covers the nanofabrication of diamond quantum chips, system integration, and the development of software for data analytics. Qnami collaborates with leading universities and industries worldwide to offer high-performance quantum sensing solutions to its customers. And then we see here the product, which in this case is the microscope for scanning NV magnetometry. And then we see here a portfolio of images and science topics they're working on. And finally, some global feedback on the company. So you see here Tsinghua, which is, let's say, Southeast Asia. You see Northeastern University, you see Stuttgart in Germany. So you have, let's say, all continents covered with feedback about the company. The company itself is located in Switzerland, in Muttenz, which is close to Basel, to the German and French border. Now, that is the basic about the company. Let's quickly dive into the products. So let's see, or maybe before we do that, let's dive into the technology, because I think that's what we are all here for. That's the interesting part. So quantum sensing. What is a quantum sensor? It is basically a sensor, and you know sensors from your real life. I worked in a sensor company previously that was making temperature and humidity sensors. You know them from, for example, your car. If you're looking in the car, there's this little display which tells you the temperature. You might have in your living room sitting one of these clocks with a thermometer integrated, which tells you the temperature of your room. So these are classical sensors. They're basically using semiconductors. So they're using the same, more or less, technology that is in your phone, that is running the chips in your phone and your computer, to measure the temperature. And by the way, also in your computer, also in your phone, there are these temperature sensors in there, and they're being used to throttle down the chips. So when your computer is getting too hot, and to avoid that it overheats, it will clock down the chip speed, the operations of your chip. And this is just one example of a classical sensor. There are other sensors. You have acceleration sensors, light sensors, all types of sensors. But usually they are using collective phenomena. They are using the same kind of technologies that are sitting inside your computer. They are based on semiconductors. And with that, they are different from quantum sensors, where quantum sensors are usually using single quantum systems. So like really the tiniest systems that you can think of that nature has, quantized systems, like atoms, for example, to measure something. In this case, this specific case here, they use NV sensors. So these are, let's say, impurities that are created inside diamonds, artificial diamonds. And because they are sitting in this diamond lattice, which is a crystal, so in a diamond lattice you have carbon atoms that sit at very specific positions, and that's how they create a diamond. This is interesting, by the way, because if you are taking the same atoms and order them differently, then you have charcoal, for example. So in a diamond, they're sitting in this very specific configuration, so on a very specific lattice structure. And in a pure diamond, there's nothing else. You will only have carbon atoms that are sitting exactly like this. But now, in these specific cases here, you introduce an impurity, so a different atom than carbon. And with that, you're creating this NV center. And with that, you can now do some quantum physics, because of the reason that basically this impurity behaves different from the whole other crystal. You can control it, and you can basically talk with a single atom or with a single atom compound, like the impurity atom plus the carbon atom. So you can talk with that. So how do you talk with it? Well, you can actually use light to probe it, because the diamond is transparent for optical wavelength. So you can use lasers from the green spectrum to the basically blue spectrum, or violet spectrum. You can see through the crystal with all of through the diamond with all of these colors. And now you can tune a laser to have exactly the wavelength that it activates this NV center. So you can basically tune the NV center. You can excite an electron within this impurity from a ground state to an exciting state, for example, by using this laser. And now this impurity, it also has some magnetic properties. And these properties, they are related to the energy of the state. So let's say you have two magnets. In one case they are repelling, and in the other case they're attracting each other. And that also means they have, if you put them on top of each other, they have different energies. In one case it will be, let's say, you need to spend some force to pull it away from the other magnet, and in the other case you basically you don't need to spend any force because they're repelling each other naturally. And very similar to that, let's say on a high level principle, of course on the quantum level it looks a bit different. These NV centers, they can have different energy depending on their magnetic surrounding. And that's actually how you can use them to measure magnetic fields. And we've talked about that before. There are also other companies that are using these diamonds and the NV centers in diamonds to measure and probe magnetic fields. If you haven't seen those videos, check out the Hidden Quantum Champions playlist on our YouTube channel after this video, of course, where we talk about other companies in that field. Now, the thing that is very particular to Qnami is now they have gone a step further. They didn't just integrate those into, let's say, into diamonds, these NV centers. They even integrated this NV center diamond into a lever, into a cantilever. And that's what you can see here. So it looks like this. You have this bar structure, and then on the top there's this little tiny tip here, which has this diamond NV center in it. So now you can shine a laser on it, and you can measure in this very tiny surrounding of this tip here the magnetic properties. And you can move this tip around, and thereby you can probe the, let's say, local magnetic properties of this underlying material here with a very high precision. This is basically a combination of using the NV center diamond and the so-called scanning probe microscopy technology, or which underlying is an atomic force microscope. So what is an atomic force microscope? Very briefly explained. You take a tip, you create in a way a tip that is atomically sharp. You can, for example, take a tungsten wire and you pull it apart, like you stretch it, and at some point it rips apart. And what it leaves at the end are two very, very sharp tips. They're of course also very fragile. And you could use, for example, one of those tips as such a structure here. So you would have to attach it to a cantilever, and then you could go with this tip and this cantilever here, and you could let's say, probe the underlying material. So you would have this cantilever. Why do you need the cantilever? It is to measure the properties of this tip. So let's say you have a material down here and you have this tip and you have a cantilever attached to it like this. And now when you are moving closer, so let's say the cantilever is like this, you are moving closer to this material and you're pressing. You see that the cantilever, which is my arm in this case, is changing its angle because here the tip cannot move any further, right? And it's changing its angle. Or it could also go like this, right? Because you are basically moving down with the one side of the cantilever, and on the other side you are hitting the surface, more or less. Of course, you're doing that at very, very tiny movements. You're using so-called piezo elements for that can move within nanometers of precision. So you're moving in very tiny steps, and the forces that are actually applied are very, very small. And then you're using a laser to shine on this cantilever, like shown here in this illustration. So you're shining the light at an angle, and a very tiny movement of this lever creates a movement of this laser beam on a projected surface. So if you had the laser beam coming in from this direction, being reflected from the lever and going up to the other direction, and now you're bending the lever a little bit, then of course you get a leverage effect on the trajectory of your laser beam, and that's how you're measuring this. Now in a classic so-called atomic force microscope, or AFM, you're basically doing that. So you're just measuring the force. So you're going here, you measure, then you're moving the tip a little bit further, you're doing the same measurement again, you're moving the tip further, you do the same measurement again. That's called the that's called the probing, right? So you're probing every single point, and thereby you create a map. And this can be a 2D map, and it takes a long time to probe a surface that is like millimeters by millimeters, because you're moving at that very tiny fractions. But it allows you to actually resolve the material surface at a very, very fine resolution. So if you, for example, have graphene flakes, you can really see, let's say, exactly the border of the flake, and then also you can measure how thick the flake actually is, because you're running from one edge to the next, and thereby you can do that. And actually, if you study physics in Aachen, in Germany, you can even do that during your physics lab course if you're lucky with such a system. Now, this is called atomic force microscopy, and there's also one where you use the electric properties. That is then scanning tunneling microscopy. And in this case here, you are using now, besides the atomic force microscopy, so the, let's say, elongation of this cantilever, you can also measure the magnetic properties. And that's very important to understand. So now you can measure the topography of your material. So like, do you have little bumps? Is it a flat surface? How does the surface look like? And on top of that, you get some information about the local magnetic properties of your material. Like, for example, if you have some atom here which creates this magnetic field, you can measure, let's say, the distance of these atoms on the material and where they are exactly positioned and how the magnetic fields are related to each other. And that is a very, let's say, useful information, and I will explain to you in a second why. And that's when we talk about the applications. So there's a lot of research applications here. So these systems that they are building, these tips that I was just talking about, they are used already in many labs. And I think there's a lot of papers related to this here. But what is important is, the further we go into technological development of our society, the more we have a need for new materials to do new applications, and also quantum materials where there's like specific quantum properties. So you have to have very clean materials. They have to they're manipulated on a very tiny level, and there are different things that you can do with it. So here's just an example of let's say a crystal, and what this crystal could look like. Now you are seeing the magnetic properties of this material. So you're seeing that the magnetic field here, where you have this yellow region, is aligned in one direction. And then here, where you have this purple or dark region, it's in the opposite direction. So like the north and the south pole of the Earth, which have magnetic field attached to them. There are also magnetic fields here, which are pointing in different directions, and you see those altering like this here. So you have up, down, and so on. And you see that they create this pattern. So you're not only having those lines, they also have this zigzag in it, and then you see they have these diamonds related to them. And that has to do with how basically the crystal is being treated, how it's being created, and that can be of very valuable. That can be a very valuable knowledge point, because you not only can create these materials and check their quality, but you can also create processes to make materials that have a very specific property. Now, why is this important? And there I want to skip quickly these 2D materials. It is important because memories, so the memories in our computer, are very, very dependent on magnetic fields. Now, how is that? So let's look a little bit into the history of computer technology, into the history of our modern digital age. Now, for the younger viewers, you might not know that anymore, but the people that have been around for a while, that were watching, let's say, on the very old TVs, where the TVs were still tubes, you could record TV shows on a cassette. And a cassette, as in like a little, not so little, a black kind of box. And in there you had a tape, basically 2 spools, and one of them was kind of winding in one direction and the other one in the same direction. And then you would have basically a magnetic band running from one to the other. And there's a reading section in between. And this magnetic band, as it says, has magnetic sections on it that could be polarized in one direction. And with that, you can basically encode information. So you can either have the magnetic field point in this direction or in this direction, and then the sensor is reading it, and thereby it reads 1 or 0 bits. And the cool thing about this is you can store information with these magnetic fields without any current. So you don't need to constantly apply them with electricity. You can put them in a shelf and they're sitting there, and you basically keep the information. This is true until you heat them up to a specific point, which is the Curie temperature. Then they basically lose their magnetic properties. It's very similar to like a little metallic nail that you can magnetize with a magnet. If you hit it often enough on the table, it will at some point lose its magnetic orientation again. The same is true for these systems. This has evolved quite a bit. So at some point you had this floppy disks, and then at some point the hard disk drives have been invented. So now we have these still in the data centers, in the big data centers. We have these rotating disks that have very tiny magnetic unit cells on them, and you basically magnetize them if you want to write, and you read out by basically measuring the magnetic field, and you rotate those disks so you can basically sample on different spots. And that's how, even in today's modern data centers, the huge amount of data is being stored. You might also know from your bank card, on the back side of your bank card, there might be a black stripe. This is also a magnetic stripe that is storing or encoding some type of information that the cash machine, the ATM, needs in order to know that, okay, it's your account, it's your card that is being read right now. Now, with our growing demand for data, these very similar to actually the transistors in your computer, these magnetic cells, they have to become smaller to actually store all of this data, because you don't want to have a hard disk drive which is like this. You want to have a small one which you can put in a standard housing, which you can put in your compute rack. So that creates a demand for the shrinking size. So basically like a Moore's law that we know from transistors, where the transistor size is shrinking and hence the chips in our computer are getting more and more powerful. We would need the same thing for magnetic domains. There are ideas of how to do that, and this is this idea of MRAM, so magnetic random access memory. And the question is, okay, how do we read those out, and how do we also control that these systems, like in the R&D phase, how do we control that these systems actually perform the way that we want them to, but then also going towards industrial application, how do we actually read those out on scale and how do we measure those? And here you can see examples of measurements of such a system where you basically have, here it says below 100 nanometer scale of these unit cells here. So these are these tiny dots that you can see here. And these dots, they all encode some information, similar to a QR code that you can look at. And with your phone, you can scan it and then it has some information in it. Here you can also store information on these 100 by 100 nanometer tiny magnetic cells, and you can orient them either to one direction or the other direction to have them 1 or 0. And such a system, such a NV probe could actually be used to read those out. So maybe in the future, we will see these systems being deployed in such a storage system at scale. There are other things as well. So there's antiferromagnets, there's spintronics, nanomagnets, and many, many more things. I don't want to go through all of these now because it would take way too long and the video would get too long. But if you're interested in that, I encourage you to check it out. The last thing that is also very interesting is superconductors. So superconductors are materials that basically we know them for having zero, let's say, resistance, so they don't dissipate current into heat, but actually they are defined by their magnetic properties, and they're type 1 and type 2 superconductors. There's a lot of research because we still don't fully understand those materials. And again, because of the fact that their magnetic properties actually what is defining them, being able to measure those is very interesting. And here you don't only need, let's say, what we had before, which is an atomic force microscope that you can use to kind of sample on these very tiny regions and these very sensitive magnetic fields. But in addition, you also need a cryostat, because usually these materials, they are not superconductive at room temperature. So the setup is a bit more complex, and that leads us to the products. So here we see Prometheus Q, which is the scanning probe microscope that I was talking about before. So basically you have the microscope here. There is a basically power supply and measurement unit, which measures the currents and probably has all the amplifiers and stuff in it on the side here, and also the data acquisition unit. And then you see the software that basically outputs you the image here on the screen. And that's what the setup looks like. And you can basically, download some material here about the system. There are also some explanations here of how it works, and some of the important technical benchmarks of the system. There's also something here about the software that they deliver with it. You can download further material. And there's also a version with it that comes for low temperature environments, which you can see here. So it goes into this cryostat. You can cool it down and then measure at lowest temperature, 2.5 Kelvin, the magnetic properties of your material. Also for some materials that have a very low Curie temperature, that might be interesting, because at room temperature they might behave chaotically, but at low temperatures they have this spin orientation happening. Now, on top of that, you can also buy the probes themselves. So the diamond probes, you can see one of those here. So this is, I guess, a scanning electron micrograph. Very, very cool. Like you see the tiny tip here. Unfortunately, there's no scale bar provided here, so you cannot really see how tiny this is. But I guess we are talking in the, let's say, micrometer range to then even nanometer range here for this image. And you see you have this lever here where the laser beam is going to hit. You have the tip down here, and you have some attachment over here, which you can then probably attach to your microscope, which is still microscopic, but at least something that you can manipulate, where this is kind of welded to. That's at least how I would assume this to work and to be like. You can also see some prices and packages down here. So these things are not something that you put into your private repertoire. You see one of them is 2.5k Swiss francs, but still I think for research this is probably a very good pricing. Here's also some information about how these are made, I guess. So you see you have the cantilever, and it says something about the implantation energy. So I guess that's how these tips are being made. So you're using an ion implanter to basically shoot an ion into the crystal at a defined energy, and that tells you something about how deep the ion will penetrate into the crystal until it gets stuck. And that's basically your NV center in your ultra pure crystal. And the higher your energy, the further it goes in, right? So you can see here 6 kilo electron volt. So this is basically the energy equivalent of taking 1 electron and accelerating it at 6 kilovolt. So just as a reference, your battery has something like 2 or 3 volts. Your wallet at home, the power outlet at home has something like 200. And this is 6 kilos, so 6,000 volts that is being used to accelerate in this case an electron, but for an ion it might be a little bit less. And in the other case you have 12 kilo electron volts, so double of that. And you can see that in one case it goes in 10 nanometers and in the other it goes in 18 nanometers because of this higher acceleration. And yeah, there are some more specifications here. And this is what the unit looks like that you would put into your microscope. So you have this chip here, which has these connection areas, probably some electrical connection areas here. And then you will have the tip somewhere here at the very front. So very, very tiny cantilever. And then there's the tip on there as well. And that is then going to be approached to the sample. And as a comparison, this is a normal Swiss franc coin. And I mean, there's some more. There are some other systems as well. So here you see the MX Plus quantilever, with some more information about it. I will not go into the details of all of this for now. They also sell the accessories, so basically the power supply and the sample holder. This one can apply some magnetic fields, which makes sense because obviously they are working in not only measuring the topography but also the magnetic field. So you want to be able to also precisely apply a magnetic field. And I mean, Switzerland is very good at building precise mechanics, like watches, for example, right? And this is a case where you build some very precise mechanics for the lab, which then also goes along with very precise magnetic fields. And you can read all of the information here. I spare you with this for today's video. And then there's also some power supply. So you see here microwave electronics that you can get as a single unit from them as well. Besides that, there's a software part, right? So how do you actually interact with the microscope? How do you read the data? Which is, I guess, what this is about. And then finally, there's some foundry service, which is also very interesting. So not only can you buy from them the tips and the microscope, so let's say going up in the integration stack, right? So the key invention is this tip, this atomic force tip with the NV center in it. And from there up, you can go all the way into a full stack atomic force microscope with this diamond tip with the laser in it to actually measure the magnetic properties. But they also go down in the integration stack to say, okay, if you have something that you want us to manufacture, for example, some structure with NV centers in it on a chip, then we can also do that for you. And that's this Qnami foundry service as well. And they have a pilot line, first diamond sensor pilot line worldwide. You can see the different services in here that basically form the foundry. So they have a lithography station in there where they can go down to 20 nanometers resolution. So very, very tiny devices that they can make. They have an implantation mask. So this is for the ion implantation, I guess, to kind of create the NV centers. They have the NV diamond. Then there's on-chip sensors, and there's reactive ion etching, which you need in order to create those nanostructures that I think we've seen before on the images. I don't know if there's something on here as well. And you need to create those tiny tips, for example, here in different types of processes. Good. So that's about this. There's also a news section, which we just very briefly go through. I'm recording this in April of 2026. The latest news here that we can see here is from March 2026 about the APS Global Physics meeting, which they are present at. But you can see there's other stuff, March 2026 coming in here. So this is very much up to date and very active. And then as per usual, we also want to quickly check out the company profile, see who are the people behind this. So it says, and what are the values of the company, right? So supporting advances in science and new technologies. At Qnami, we develop fundamental new technology using quantum mechanics. The control and measurement of the state of a single electron enables us to measure what could never be measured before. We call this quantum sensing, and we are enthusiastically developing this technique to support advances at the cutting edge of science and technology. Building a future together, the world is experiencing a quantum revolution with astonishing potential for innovation and growth. Qnami is a venture capital-backed company. We are taking a lead in this revolution, aiming to be a thought leader in our industry. And then we see here the values: sharp foundation, human connection, and scientific expedition. And then quantum technology made in Switzerland. It all started with the lab of Professor Dr. Patrick Maletinsky, I hope I pronounced that correctly, at the University of Basel. Known as a cluster for life science, Basel is a vibrant city that offers great opportunities. Since 2016, we are working enthusiastically to build a global quantum industry from this city in the near heart of Europe. And then we see here long-term partnerships and collaborations. Of course, as a Swiss company, they do collaborate with Zurich Instruments. We have made a video on Zurich Instruments previously. You also see there's academic connection here to the University of Basel, but also collaboration within Europe. So you see Thales, for example, which I think we've also talked about before. The PSI, which is here in Switzerland, Fraunhofer in Germany, and many, many more. I don't want to go through all of these now. There are also some awards that the company got awarded to. And yeah, the usual information down here, how to get subscribed to the newsletter, and so on and so forth. Now, quickly about the people, the team behind the company, right? So this is us. We are both business and scientific minded. Each of us offers their top unique skills plus an enthusiastic spirit because we believe in what we do. So here we see the team. The company is, I think, growing very well. So it started in the lab, right? And now you have all of these people here that are contributing with different backgrounds. So you see optical engineering, product management, finance, HR. So all the functionalities that a company actually needs with all the different people. You have the co-founders on here, application scientists, head of finance. So many different people that all contribute and that basically build this forefront technology, I would say, of quantum sensing that probably becomes very relevant, not only in the science community, where I think it is already relevant, but also very soon, I would guess, in the industry, because what they are doing is very interesting, even for today's silicon industry. What do you think about this? So do you think that we will see these magnetic memories developing? Do you think there are other applications that are even more important where this technology could play a role? Let me know down in the comments below. I'm excited to hear your thought on that. And I'm looking forward to see you in the next video. So if you have not subscribed, please make sure to subscribe to this channel. I'm looking forward to see you again. Until then, bye-bye.